Okay, now let's see if Syed is here. Testing. Testing, testing. There he is. Hi, Syed.
Hi,
How are you
how are you?
doing? Not bad.
I'm doing good. A
Okay,
quick
so
question about
yeah,
the grading for the assignments. Are we waiting for another TA before we start grading?
I was waiting, but I was expecting some information today, which I didn't get. So
Okay,
I'm going to open the grading today, and I'll send an email about it.
okay, right. Should I let them in?
Yep.
Okay.
Okay. Okay. Morning, everyone. Let's. There's a couple of minutes left before before we start, so let's take some questions. Maybe there's a way for me to disable the waiting room for now. Should I do that, or do you think it's not a wise idea?
Yeah, I guess at 12:10 we can disable it so everyone can just
Do
automatically join.
do you have the power to re-enable it?
Yes.
Okay. So whenever you're ready, we can re-enable it.
Okay.
I'm just curious, some people were asking on the chat whether there's a YouTube link. So does that mean that you cannot see the messages in the chat from before you joined? No. So it means that you can see, you can just scroll up and see them. Oh, you cannot. I see. I see. So that's the problem. I don't know. Yeah, doesn't seem to be a way of making sure that you can see the previous posts.
On the top left, though, there's a live on YouTube button. If you click on that, you can see the link.
Oh, very good point. Yeah. Did everyone hear that? Just click. It's right there, live on YouTube. Thank you. Does anyone have any questions before we start today?
Yeah, so Rui Chan has a question.
I see your question.
Yeah,
Rui Chan.
my question is some of the operation laws. So could you please help us to recall some of these laws? Because
Well,
I'm a little bit confused
I'll
for
be doing
this.
more about that today. So hopefully what I do today will help. Anyone else?
So Dixchant has a question.
Yeah, hi. I just had a question from the previous lecture about, so when we define the equivalence between two maps and when they say we're similar, like in your notes, you had mentioned that squiggly line and then you gave us the three axioms.
Yeah.
So in those three axioms, so like I wasn't quite sure about the terminology when you say that the squiggly line is an example of an equivalence relation on a set S. Is that set the set of the two maps, or is each map considered one? Like, sorry, is that the set of like one entire map, or is an element of that set one map, or is an element of that set one, like one individual set from which a map can be formed to another set?
So what is being claimed to be equivalent here? What is
Uh,
equivalent to what? What kind of object is it that we are applying this to?
two maps.
Okay, so we have
Oh,
two
right.
things. Those things are equivalent. Okay, so the equivalence relation is on the set of those things. If you're talking about equivalent maps, the equivalence relation is on the set of all maps.
Right, and when
Maps of a certain type. These are maps from X to Y.
right, so when we say X is equivalent to X, does that mean that one set X is equivalent to another set X, or is it one map is equal? Oh, no, that'll be one
We
map.
already discussed, we already settled that. Do you agree that
Yeah.
we're talking about equivalence of maps? That
Yeah,
it
yeah.
is the
Oh, yeah.
maps which are equivalent? Yeah. So X, squiggly line X means that any map is equivalent to itself.
Yeah, yeah.
Okay, but the point is that the idea of an equivalence relation is very general. You can put an equivalence relation on anything, any set. It doesn't have to be a set of maps. Okay, let's start. Okay, so, okay, very good. So we already started the second section, which is about going beyond sets and maps. So we're trying to equip a set with an algebraic structure. Okay, and I gave a bunch of examples. So we have this thing is just a set A, and it has an algebraic structure. It has a particular kind of algebraic structure, which is called a binary operation. It takes two inputs. The inputs are elements of A. It combines them and gives you an output, and the output is also in A. So it goes from A cross A to A. This is a map, right? This thing is a map from A cross A. It takes two elements of A and it outputs an element of A. That's what a binary operation is. And there's no rules on this thing. So even something this crazy like this could be considered a binary operation. It's just a binary operation that doesn't really satisfy any nice properties. Now, the most typical property that we require from a binary operation is the associative law. And that just tells us that if you combine, it's like if you multiply numbers, three numbers, it doesn't matter which order it doesn't matter whether you multiply the first two and then multiply the result with the third, or if you multiply the second and third and then multiply that with the first. So this is not about order. It's not about it's not about the order of the elements. That's commutativity. It's really about the order in which you combine elements. Do you combine these two first and then combine this with this, or do you do it in the opposite order? The equality of these two things is the associative law. And then we can put even more structure. We can put an identity element in, which combines with every other element to do nothing. And that's what we call a monoid. Now, the first important one, the one that you have to know about for now to go forward, is the example of a group, and that's where you have a set, you have a binary operation which is associative. It has an identity, and every element has an inverse. Okay, so these are very plentiful, and we're going to start by studying a little bit of these. And we already saw one, which is the permutations of n elements, or the bijections from a set to itself. Okay, so if you, let me, just to avoid any kind of confusion, these are bijections from a set X to itself. Okay. So this is in the case that X is equal to Bn, which remember is the set 1, 2, 3 all the way up to n, then bijections from Bn to Bn is known as Sn, the group of permutations on n elements. Permutation is just another name for a bijection from the set to itself. Okay, so this is an infinite number of examples of groups, because there's one for every n. Okay, and there's a even simpler type of structure where we require an additional law, an additional axiom, which is that it should be commutative. So this commutativity means that A star B is equal to B star A for all A and B inside the set. So this is the commutative law, and groups normally, unless you assume it, it's not necessarily true that it's commutative. In fact, this permutations is definitely not commutative. If you permute according to one particular recipe, and then the permutation group, you could think of it like this, that you have three elements, and the permutation is like a diagram, like the way we drew it, with going from top to bottom, right? And then if you have another permutation, you can stack them on top of each other, and what you get is a final permutation, right? So this is the group law, or the group multiplication is just stacking the permutations, doing one after the other. Okay, and it matters in which order you do them. If you put the red one first, right, ups. So if I grab this, yeah, anyway, you can do it yourself. So if you put the red one on top of the green one and compose, you will get a different result. So this is not equal to if you combine them in this way instead, doing the red one first. So then we'll get this example, right, which is not the same. So we see that F compose G for bijections from X to itself are not necessarily equal to G. So this is not necessarily true. Okay, so this is a non-commutative group, but if it is a commutative group, we call it an abelian group. Okay, so let me give you another example of a group before we move on to rings and fields. Example of a group. Actually, of an abelian group. Okay, so I'm going to give two examples. So the first one is the integers. Now, the integers, we're all very familiar with the integers. There's two binary operations on the integers, but I want to focus on plus, the addition operation. So I want to take the integers together with the addition operation, and this has an identity element. And I remember that an identity element would be an element such that if I add it to any number n, the result will be n. So this element plus n equals n. So the only element that satisfies that is 0, and 0 is the identity element for this group. And then there's an inversion map, which basically takes an integer and sends it to minus n. So we have a group, we have a set, we have a binary operation, right? We have the identity element for the binary operation. It's a binary operation. It's associative and commutative. Okay, there's an identity element. Okay, and then there's an inversion map. There's inverses for every element. So this is the inverse. Every element has an inverse. Okay, so we can think we can even draw them. These are the integers. And we denote it by Z. Okay. So this is an infinite set, but anyway, we know it very well. So we view this as an abelian group. Okay, so there's a very interesting construction which you need to learn right now, this week, and it is sometimes called modular arithmetic. The basic idea is that we're going to take the integers and we're going to construct from the integers another group, which is actually finite. It's almost like a child group of the main group, the integers. So the integers, we are going to be able to do an operation on them to produce other examples. Okay, and the way that we're going to do this is by defining an equivalence relation on the integers. So we will now construct some finite groups from the integers. Okay, and the way that we're going to do it, the strategy is that we're going to define an equivalence relation okay, and this equivalence relation is going to break up the integers into some subsets, which partitions Z into subsets. These subsets are called equivalence classes. Okay. So we're going to divide them into sections, okay? But we're going to do it in a very careful way, in such a way that that the group law or the binary operation, right? It will be compatible with the partition into subsets. So what I mean by that is, it's like we're going to divide all the integers into various species, okay? And we're going to look at how elements from one species adds with elements in another species. So we're going to basically see that if you take someone from one species and you take another one from another person from another species, right? And if you combine those two individuals together to get another element, that will be in a third species, okay? And what we're going to see is that it doesn't matter which individuals we picked from that species. If I picked another person from the same species and another person from the same species, and I combine them, the result may not be the same, right? But it would be of the same species. So what do I mean by that? So let's say that we have one species and another species, right? And we have a bunch of integers in one species and a bunch of integers in another species, okay? And we notice that if we take an individual from this species and we take an individual from this species, and if we combine them using the plus operation, okay, what we're going to get is an individual which is part of some species. That's obvious. Okay. But the interesting thing is that if I change the original person the original people that I used, that I combined. So for example, if I take this individual instead, and if I take this individual instead, and I combine them, okay, I'm going to get a different individual, but the individual will be in the same species as the result from last time. Okay, so, and I can continue this for all possible pairs, right? So if I take this individual and combine them, we're going to get an individual in the purple species. Okay. So as a result, this is what I mean by saying that it's compatible with the partition. Okay. As a result, the partition itself becomes a group. And just to avoid confusion, I'll just put a couple words here. The partition itself, i.e. the set of equivalence classes, becomes a group. Okay. It's kind of like, yeah, it's kind of like when you're making, this is something that's happening a lot these days. There's a lot of work nowadays being done in the breeding of hot peppers. They're developing hot peppers, and they're always developing hotter and hotter peppers. One way of doing that is to take two peppers of the same species, right? But they have different qualities, different varietals, and then you combine two of these plants, and you create a new varietal, a new cultivar. Okay, and some of these things are well known, that if you take a hot pepper of one type, like a jalapeno, and you take a hot pepper of another type, like a Scotch bonnet, then it's understood that what you're going to get is something which is not like either jalapeno or Scotch bonnet, but something else. And the point is that it doesn't matter the individual that you use, the individual plant, right? It's all that matters is that that plant is a pure Scotch bonnet and the other one is a pure jalapeno, right? And that means that the breeding operation, the cross-breeding operation, it's true that it's defined on individuals, but it actually makes sense to think of it as applying to the entire varietal. So that really we only have to record that green plus red is equal to purple. Okay, so let me explain how this is done. We're going to take two elements, two numbers in the integers. So we define the equivalence relation like this. So we say that if n, let's say that if, okay, so this is how we define the equivalence relation. So we first choose a positive integer, which we're going to call n. Okay, and we're going to obtain, so we'll define an equivalence relation for each n. So this is going to be the equivalence relation for this chosen integer. We're going to fix it, and then for the rest of the discussion, it's going to be fixed. So for example, you could imagine that it's 10. We're going to fix the number 10, and we're going to define an equivalence relation which uses the number 10, which cares about the number 10. And we'll say that if a and b are integers, then a will be equivalent to b when b minus a is divisible by n. Okay, so for example, if n was chosen to be 10, okay, then we can say that 1 is equivalent to 11. And 11 is equivalent to 21. Oops. Yeah, to 21. And minus 5 is equivalent to 5. And 0 is equivalent to 10. Okay, so as long as the two numbers differ by a multiple of 10, we're going to consider them to be equivalent. Okay, now, so for example, if I write some numbers, I'll continue with this example. So for example, if I write 7,863, what is this equivalent to? Well, it's equivalent to it's equivalent to 7,873. That's definitely true. But we can choose an equivalent integer which is a lot smaller. We don't anymore, because of this equivalence relation, we don't need to work with large numbers anymore, because we also know that this is equivalent to 3. Okay, because all of this stuff here, all of this stuff, 7,860 is divisible by 10. So all of that is equivalent to 0. right? So 7863 is equivalent to 3. And any integer is equivalent to one integer in the list from 0 up to 9. So in fact, every integer is equivalent to a unique element of 0, 1, all the way up to n minus 1. So here there are n elements here. Okay. And you can see that the properties are preserved. So any number is equivalent to itself because the difference is 0 and 0 is just 10 times 0. We can also see that if A differs from B by a multiple of 10 and B differs from C by a multiple of 10, then A must differ from C by the sum of the two multiples of 10, which is also a multiple of 10. So transitivity holds. And then you can see that the order here doesn't matter, right? If B minus A is divisible by n, then A minus B would also be divisible by n. So it is reflexive as well. So this is an equivalence relation, and it divides the integers into subsets. So what do these subsets look like? Well, let's say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, minus 1. Okay. Right, so we can see that this element is equivalent to this element. Is equivalent to this element, and so on. I just want to make sure that there is no confusion. So all this here, these minus 10, 0, 10, and 20, this forms an equivalence class of 0, and it continues. Okay, every multiple of 10. This is the equivalence class of 0. And then all of these are the equivalence class of 1, and so on. Okay, and so you can see that all of the integers, the entire set of integers, has been partitioned into 10 subsets. Okay, the resulting equivalence classes are called 0, 1, all the way to n minus 1. And we use a square bracket to denote the fact that, you know, this represents not just the number 1, but it actually denotes the equivalence class of the number 1. And in fact, the way the notation works is that this is actually equal to the equivalence class of 1 plus n, right? So if you put multiples of n inside the square brackets, they die, they go away. This is the same thing as the equivalence class of n and so on. But this is a finite set of size n, and we have a name for this, which is z mod nz. And because it arises so often, we sometimes just call it z sub n. Okay, so all I've explained so far is that we're going to use a number, like a fixed number that we're going to decide on first, like 10. And using the number 10, I can break up the integers into 10 disjoint subsets. We get a partition of size 10, and we get a set of these subsets, 0, 1, up to n minus 1. Okay, and this subset, this set of equivalence classes is called Z mod NZ. And the interesting thing is that this forms a group. It inherits a group structure. So let me explain that, and then I'll start taking questions. So this finite set inherits the binary operation, the group, the operation plus. Okay, and so it's exactly this idea, right? So here now, what does green represent? It represents an equivalence class, of integers, which all differ by a multiple of 10. And this is a different class. So this could be the equivalence class of 1. This could be the equivalence class of 2, right? And what I want to do is add them together. So if I add 1 plus 2, I'm going to get 3. So this is going to be in the equivalence class of 3, right? So let me just write this here. So in other words, if n is equal to 10, then look what happens. So 1 plus 2 is 3. But if I now replace 1 with something equivalent to it, like 11 or 211, and 2 is equivalent to 12, then the sum of 211 and 12 is 223, which is equivalent to 3, right? So what you see is that it does not matter from the point of view of these equivalence classes. It doesn't matter which representative you choose from that equivalence class. I could choose 1 and add it to 2. I could take 1 plus 12 or 211 plus 2, right? As long as as long as the first person is in the first group and the second person is in the second group, the sum will be in the third group. That's the point. Okay, so that is to say, if we define the sum of equivalence classes as follows. So the equivalence class of A, now I want to write the new addition law on our new set. If I add this equivalence class to the equivalence class of B, right, I need to give an output here. So what am I going to do? Well, what I'm going to do is I'll just add them using the usual operation on the integers. That will be an integer. And now I'm going to take the equivalence class of it. Okay. So here, what I have a potential definition, because I'm saying, what I'm really saying when I draw this formula is I'm saying in order to define, so I'm trying to define this. This operation, right? So what I do is the following. I say, I'm trying to add two equivalence classes together. So choose a representative A of the first class, choose a representative B of the second class, add them together as you would normally do, and then take the equivalence class of the result. So this is a viable option, but the problem is that you made some choices. So in order for this to be a real definition, for this to be a true definition, or a correct, or a definition, we must check that it does not depend on the choices of representatives A and B. Okay, so in other words, if I have a different, so let me write it like this. So if we have a different representative A prime, and if we have a different representative B prime of the same class, same species, then we must show that the equivalence class of A prime plus B prime, where we do the normal addition of these, is actually equal to the result of doing it for A plus B. Okay. And this is pretty easy to do because we have two assumptions. Okay. Assumption one means that A prime minus A is a multiple of N, some integer. Number two, the second assumption implies that B prime minus B is some other multiple of N, right? And from these two, we can imply, we can see that A prime plus B prime minus A plus B, okay, is equal to, so here I can use, everything that I know about the integers. This is the same thing as A prime minus A plus B prime minus B, and this is K1 N plus K2 N, and this is K1 plus K2 times N, which means that A prime plus B prime is indeed equal to A plus B. The equivalence classes are equal. Okay, so as a result of this, we get a new set. This is a set of size N. We have a new operation, which I'm just going to call plus. And then we need to worry about whether we have an additive identity. And the identity element is kind of obvious because we just take the equivalence class of 0. And I'll leave it to you to check that this is an additive identity. And then I'll also let you check that the usual inverse will work. So the inverse applied to an equivalence class, how do I produce another equivalence class that if I sum it with N, I get the equivalence class of 0? Well, it's obvious. It's just the equivalence class of minus N. And the conclusion of all this is that we get a new abelian group. Normally, we don't bother writing all of the structure. We just write the set. The name for the set is Zn, and this is called the group of integers modulo n. Okay, and we have one of these groups for every n. Okay, now don't get confused because we know that the integers have another binary operations, which is the multiplication, but we're not talking about that yet. That's what's coming next. Okay. So okay, now any questions about this?
Okay, so Jay has a question.
Hi.
Hi.
This might sound kind of ridiculous, but for this process that we just went through in partitioning the set, could you show us what's happening with this particular example on like the red, green, purple diagram? Like where is the set of integers and how does that get partitioned into?
So here's the set of integers.
Right.
Right. And the point is that every 10th integer, right? This is the black set. And this is the green set. So there are 10 sets, right?
Mhm.
Is it clear what I'm trying to say?
Yeah.
There are these sets like 2, 12, 22, right? They form a huge set of integers, which are all, they all differ from each other by a multiple of 10. It's like a jump, you skip 10, right? So there's going to be, the first set is this one, the one that contains 0. It's every 10th integer starting from 0. The blue set is every 10th integer starting from 1, going backwards and forwards. Okay, it's like when you're playing the piano, right? The letter C, I mean the musical note C, right? It occurs evenly spaced every octave, right? So where's the letter C? Well, it's in many locations. It's an entire subset, and the set of musical notes in the so-called Western scale is partitioned into 12 subsets for the different notes, for the different full tones. Same thing here. And the point is that if you want, the interesting thing about this way of breaking up the integers is that if you take anything that's green, right? What happens when you add 1 to 2? 1 plus 2 is, last time I checked, it's 3. Oh, that's too close. 1 plus 2 is 3, right? So that means that if we combine these two, it'll give this as an output, right? But the interesting thing is that it doesn't matter which representative you pick. If you pick one, something green like -9, and you pick something red like 12, then -9 plus 12 is going to be in the same subset as 3. It's going to be, -9 plus 12 is going to be 3 again. But anything blue plus anything red is going to be something olive green, I guess, whatever this color is. So the point is that it's not just that the integers can be added, it's also that these different colored subsets can be added together. So green plus red is equal to olive green. Does that answer your question?
Yes, I think, yeah, I'm trying to equate that. I think that does, yeah.
I just collected them, I just collected them into their own little groups, but they're distributed inside the integers in that way. Anything else?
So Kenav has a question.
Yeah, go ahead.
Hi. So my question is, how exactly is a abelian group defined? Like, is it just that it has a natural set of?
Are you asking how a group is defined or how an abelian group is defined?
Yeah. Because if they're both abelian, like I don't like why.
Sorry. Are you okay with the definition of group?
Yeah.
Okay, so an abelian group is just a group that satisfies an additional axiom. This axiom is the commutativity axiom. So it's an additional axiom, and we don't have any additional structure. We don't have any, there's nothing left on the list, right? I don't add something to the list. It's just that this binary operation happens to be satisfying the commutative law, AB is equal to BA.
Okay.
It's a property of the binary operation. Some binary operations are commutative, some are not. If it's commutative, you say it's abelian.
Okay, thank you. And then one other thing, on this page, the one that you're on right now, that one. You have 1 plus 2 equals 3, and then 2, 2, 2, and 3 exclamation marks. Like, why are we adding those?
I'm sorry?
Like when it says 1 plus 2 equals 3, and then you have like 2, 2, 2, and then 2, 11 plus 12 equals 2, 2, 3. Like,
No, sorry.
what is that middle?
This is just this is the equivalence relation. This is the equivalence relation. 1 is equivalent to 211. 2 is equivalent to 12.
Oh.
And 3 is equivalent to 223.
Okay, thank you.
Okay. Okay, so I'm spending a lot of time with this idea just because it is so fundamental. Okay, so I just gave you a whole bunch of different groups. I gave you a huge family of non-abelian groups and a huge family of abelian groups. Both of them are all of these groups are finite groups. And yeah, by the way, just as a note, when when A is equivalent to B in the sense that I just defined, they usually write it in the following way. A is congruent to B mod n. That's the terminology that is used, because they need to tell you, they need to have a notation for the equivalence relation. So they use 3 lines, and they need to give you the information of which integer am I picking in the definition of my equivalence relation, like 10 or 5 or whatever. And so they include it in this way. And the idea of modulo means that you're going to consider equality, but you're going to forget about, or you're going to ignore multiples of n. Modulo means that you you kind of remove or ignore a certain type of relationship. And here what we're doing is we're saying that if 2 numbers differ by a multiple of n, we're going to consider them to be the same. We're going to consider them to be in the same class. Okay, and this is absolutely fundamental to any part of mathematics, this abelian group. Okay, so we need to go beyond groups. This course is not about groups, so we need to go beyond groups. Okay, and the next step beyond groups is rings. Okay, so this will be the way that a ring works is that you try your best to put a binary operation on top of the group operation. So we start with a set. We start with a commutative. So instead of listing it all, what I'll do is I'll do it like this. So this is an abelian group. Okay, but we include extra stuff. So the extra stuff is going to be a new binary operation, which I'm going to denote by a dot. Okay, so this is an additional binary operation. Okay, and when you study rings, you don't necessarily assume that this one is commutative. This one may not be. It may be non-commutative. It depends on which ring you're talking about. Okay, and this must be associative. So let me write that. Associative binary operation. And this one is called the multiplication. And this one is called the addition in the ring. Okay, and the important thing is that we are going to insist that the 2 binary operations play nice with each other. Okay, so in other words, we're going to require a compatibility axiom, okay, between the 2 binary operations. Okay, and this axiom is going to say that if I take an element of the ring and I multiply it against a sum, that should distribute over the sum. So it should be the same as A dot B plus A dot C. Okay, this is called the distributive law. Okay. Why do we have this? Well, okay, it's basically through experience that we know that this is an interesting thing to do. A perfect example of this would be the integers. We already saw that they form a group, but they also have a multiplication. That multiplication happens to be commutative, but it's definitely associative. And we know that, that the distributive axiom holds, right, from our study of just numbers. So this is an example, this is the perfect type of example of the type of structure we're looking for. It's a single set, and it has two binary operations which are compatible with each other in the sense of the distributive law. Okay, one of them is a group, and the other one is associative, but it may not be a group. So with respect to the multiplication, the integers do not form a group because we don't have inverses. So like there is no inverse of the number 2 under multiplication. There is an inverse with respect to addition. Oh, I'm sorry, I forgot to put the inverse structure in here. So we know that this is a group. I'm just writing inv sub plus because it's the inverse for the binary operation plus. So this is multiplication. Okay, and it's definitely the case that there do not necessarily exist inverses of elements using the product operation, the multiplication operation. Like I said, for example, 1 over 2, okay, it is not present in the integers. Okay, now there's something that I left out on purpose, which is that you see the nice thing about the integers is that although you don't have inverses, it does have a multiplicative identity. I'm going to have to stop in a moment. So there is a multiplicative identity, which is just the number 1, right? 1 times any integer is equal to that integer. So the number 1 acts as a multiplicative identity. So we include that. This is the multiplicative identity element. So the important thing here is that we're going to do the same thing in general for rings. We're going to assume, although actually some people don't do this in some books, although it's more common to include it, we include the multiplicative identity element. Okay, so this is the structure of a ring. A ring consists of an abelian group with an extra multiplication operation, which is associative, distributes over addition, and has a multiplicative identity. And the perfect example is the integers. Okay, and the second example, which I don't have time to go into right now, is the integers modulo n. This also inherits the multiplication from the integers. Okay, and the last step we need is to go from rings to fields. And the only difference between rings and fields is the existence of inverses. So just maybe as a brief comment, just so that you know what you're reading about, is that for fields, we also, fields, these are rings in which every element has an inverse, has a multiplicative inverse, except for one element, 0. Okay, so just like in the the rational numbers, right? Any rational number has a multiplicative inverse, because if you have a over b is a rational number, then b over a would be its multiplicative inverse. So every rational number has a multiplicative inverse except for 0. And that basically explains what is a field. Okay. And yeah, so the first part of your reading is supposed to kind of cover some of the material on fields, and we'll talk about it some more on Tuesday. Now I have office hours, so I'll just stick around for the next hour for questions. But if there's anyone who has questions about what I've just said today, ask them now.
All right, so Neil has a question.
Yeah, I had 2 questions. One, so I think, I guess that might have been the old definition, but generally I thought of like the group of integers modulo n as being literally just the set of integers from 0 to n minus 1. And here it seems like it's being defined as the set of equivalence classes defined by those elements 0 through n minus 1. So is this just more like a general version of the same, of that concept, the group of integers modulo n?
So it's really the same. Because if you, like I said here, right, the equivalence classes, right, how many equivalence classes are there? There are n, and you can label them by their representatives, 0, 1, up to n minus 1. So you're saying that this group has n elements in it. You agree with that?
Yeah.
Right, and you're labeling those n elements with 0, 1, up to n minus 1. So what you are saying is no different from what I'm saying. I'm just giving an alternative interpretation for what these elements actually mean.
I get, okay, so I guess it's just a matter of, is the set of is the things within those braces, are they usually equivalence classes or are they single numbers? Because yeah, there's definitely like an isomorphism between.
They are single elements of this set, but with respect to the integers, the right way of thinking about what they are is that they're subsets of the integers.
So not just unique integers, which is, I think, sort of the way.
Well, it's not very helpful to think of them as being unique integers because because of this fact, that if we consider, the number 10 is considered to be equivalent to 0 inside this group. Like, for example, if you want to define the addition, right? What's 5 plus 5 in Z10? 5 plus 5 is 0, right? But how did we obtain that? It's because 5 plus 5 is equal to 10 in the integers, and 10 is in the same equivalence class as 0, and therefore
I guess maybe, yeah, I think it just, I guess modular addition is usually just taught as, you hit the end, you just round, or, mod it as an operator instead of, this is just, so a different way of thinking of that.
Yeah, just, I think you understand, so let's move on.
And then one other question. So this class Z mod n is obviously defined by n, but suppose you had an instance where you made Z mod 3 and Z mod 6, yes. And then would you be able to add, because everything in Z mod, everything in the equivalence class of 6, the identity equivalence class for 6, so just 0, 6, etc., is also in the identity class for 3, 0, 3, 6. So I guess maybe it's a meaningless idea, but could you like add them? Because then you would still end up with the same identity class for mod 3. So is there a notion of adding it from across different?
Sorry, your question is a little bit vague and going everywhere, but the point is that these Z mod NZs for different n's, they are different groups, okay? And if you're asking about how to relate them with each other, what you're really asking about is, are there maps between these groups for different values of n?
Right.
For example, Z mod 3Z and Z mod 6Z. Are there any maps between them that might be of interest, right? They're not the same as each other, and they're not contained in each other in any sense. They're just different groups, one for every value of n. And there may be some nice maps between them, and that's kind of what you are fishing for.
Yeah, because I guess, yeah, the set of elements would be the same, or at least all the elements in one would be in the other for certain.
Yeah, you're sticking to your guns. They are different sets. They are different groups, and you may map between them, but one is not contained inside the other in any sense. So just try to reevaluate. Okay.
Okay, so Dixchant has a question.
Yeah, hi. I just wanted to, like, this is about the proof. Could you scroll down to the proof where you talked about A minus B equals A plus B? Like, could you, yeah, A prime B, yeah, could you just go over this, especially the part where, like, I don't understand. When you say A prime minus A, like, is that
Just 1 second, just 1 second, just one
Yeah.
second. Okay, so there's formulas here, and you can stare at these formulas all you want, but you're not going to understand what's going on unless you understand the strategy of what we're trying to show. Okay, so look at this. So I'm trying to define the sum of what? What are these two things that I'm trying to sum?
integers?
No,
Integer
they're not integers. They're not integers.
integer mod. The groups of integer mod, two different groups.
Well, that's still a little bit too vague. What is bracket A? What does this mean, bracket A?
A mod of
What is it? Is it a number? Is it a collection of numbers? Which collection of numbers is it? What I'm asking, what is it? Not what it's called or anything.
Is it an equivalent? Do you call it the equivalence set?
It's an equivalence class, but what is it actually? I mean, those are names, but you know, what kind of an object is it? What is? Let me ask first. What is the thing inside the brackets? What is this A?
Well, that's an integer, right?
That's an integer, yeah. And then the brackets around A, what is this thing?
Is that a group?
So this is the integer 0, right?
Yeah.
The equivalence class of 0 is the subset minus 10, 0, 10, 20, 30. All of those integers all together form an equivalence class. They're all equivalent to each other. 0 is equivalent to minus 10, is equivalent to 20, and so on. So this class, this subset of integers is what is meant by this. This is a subset. It is a species of integer. We're partitioning the integers into 10 species. Okay, so this is a subset of integers, and this is a subset of integers.
Right.
Okay? These are like political parties. A is only a member of the political party. B is the member of the political party, and we call them representatives. So A is a representative integer of its class. It represents its species. Does that make sense?
Yeah,
Okay.
I understand that part.
So now we have a species and we have another species. These are both subsets of the integers, and we want to add them together to get another species, right? We want to explain, how do you take one species and add it to another species? How do you do it? Well, this is what we want to do. We want to say, choose a representative of the species. That's an actual integer, A. And choose an actual representative integer of the second species, B, and then add them together in the usual sense. And then whatever the species is of the result, that will be our answer. Okay.
Right.
So it's like we're taking two representatives of a political party and we're putting them together and we're getting a third political party. Okay. But the problem is that this might be bad news, right? Because maybe this species, maybe it depends on which representative we picked, right? So in order for this to be a true definition, we need to make sure that the result does not depend on the particular member of the species that we used to define it, but rather it's a property of the entire species, that no matter who we take here and no matter who we take, when we take their sum, it will be in of the same type.
Yeah.
So what did I do? I said, well, okay, change the result. So change the choice. Let's say that A prime is another choice of integer, which is in the same species as A. And B prime is also in the same species of B. And now let's try to add A prime and B prime together. Do I get the same result as if I added the original choices? Okay.
Yeah.
That's what I'm trying to figure out. So,
Right.
so how do I figure this out? Well, by definition, this species and this species are the same when the difference between these two numbers is a multiple of n. So I take the difference. I want to see, you know, I want this to be a multiple of n, because if it is, then it would imply that the species are the same, and it didn't depend on which choices I made. So I just take the difference and I compute it. I see that it's A minus A prime, but this is a multiple of n because I chose A prime to be of the same species as A. This is a multiple of n because I chose B prime to be of the same species of B. And then if I add these two together, I get a multiple of n. So the difference between the results is a multiple of n. So these are the same species.
Yeah, that makes a lot of sense. Yeah. Thank you.
Okay, you're welcome.
Okay.
I don't know how loud my sound is. Maybe I'm talking too loud. Okay, go on next.
So G Cow has a question.
Yes, Professor. Can you give a formal definition of compatibility?
So we have two binary operations, right? These are different binary operations. And this here is a law, is an axiom that involves both of them, right? You see the dot and the plus. Both of them are occurring here. So this is a law, this is an axiom, which involves both of these operations. Do you agree with that?
Yes.
So that's what a compatibility axiom is. It is an axiom that involves two algebraic structures.
Okay. And somehow, if I can set up an equation using this two operation, I can just say this is a compatible axiom.
Yeah, correct.
Okay, thank you.
But we have a particular one that we want, which is distribution axiom. So this is the axiom that we use for rings.
I just want to know what is so special about this one. Why can't we just choose?
Well, I mean, do you have a guess for why this might be a useful axiom?
It satisfies all other previous properties we just described, I guess.
I'm sorry. I mean, you know, rings are supposed to be modeling our usual number system. So it's a generalization of usual numbers.
Okay.
So the reason why this is useful is because it's true for almost all types of numbers that you know about, that you know something about. So, right?
Okay.
That's the reason, is because in principle, in practice, we find this axiom holds all the time. On the other hand, there are some sets that don't have this axiom at all because they don't even have two binary operations.
Okay. Can we have, can you give another compatibility example?
Yeah, we're going to see plenty of them the next class, because we're in the definition of vector spaces, or in the definition of fields. Well, fields I basically did already. In the definition of vector spaces, we're going to have a different kind of a compatibility axiom.
Okay, thank you.
You're welcome.
Okay, so Shu Ji has a question.
Hi. Yeah.
Hi,
Professor. I
Hi.
have a question about the definition of rings. So when you talk about the definition of rings, you first so first it inherits the property of abelian group, and then you define a multiplicative like operation.
A multiplication, yeah.
Yeah, exactly. And in the end, you say it also have a multiplicative identity. So
That's
I'm
right. That's what's
I'm
here. Yeah.
wondering, is it can it be proved, or just it's by definition we define it?
You mean, can you prove that a ring has a multiplicative identity?
Yeah, exactly.
No, it's a necessary axiom. If you don't have it, actually, some people, what they do is they define, so they use, oops. Oh. Some people, what they do is this, they say that there's a letter I in ring, and letter I is the first letter of identity. And they relate it with 1. And then they take the letter N, which is the first letter of negative, and they relate it to the additive inverse. Okay.
Oh,
And so what some people do is that they define something else, which is called rig, and they also define rung. And these are rings, but with no negative, no inversion, and this one does not have an identity.
oh,
So these are yet more mathematical algebraic structures. So if you don't have a multiplicative identity, it's called a rung, and if you don't have an additive inverse, it's called a rig.
oh,
But
yeah.
but these are not as, you don't encounter these as often as you encounter rings. Rings are really the backbone of algebra. They are present in every part of algebra and geometry. Rigs and rungs, well, they do occur, but they're not as important as rings.
Oh, I see. So
It's like cats and dogs. You know, they're very important. Rings and groups are like cats and dogs, very important. They appear everywhere. Some people have iguana as pet. This is like an iguana. And this is like, you know, I don't know, whatever, some other exotic bird, you know.
So rings have some like general and universal properties, so we need to study it. Is like,
Yeah, you need to know what is a group. You need to know what is a ring. You need to know what is a field. Those are all fundamental. They occur everywhere in mathematics. It's like the hardware. It's the hardware on which everything runs.
oh, I see. Thank you.
You're welcome.
Okay, so Gurmanjot has a question.
I just had two quick questions. So I was like, you know how you should like the
You're breaking up for some reason.
property that was one of the compatibility distributed the right distributive property also have to be one of the requirements, because when I like did some research, I found that usually like that was one of the definitions of ring as well, where right
Sorry,
like
just stop. I can't make heads or tails of what you're saying.
As well. So
Stop. Okay, wait. Turn off your video and try again.
Do you clearly hear me, or?
I cannot hear what you're saying. You're all breaking up. Turn off your video and ask it again and try to be brief.
Okay, all right. So my first question was, would there not also be like the right distributive property for rings? So like in this case, it would have to satisfy B plus C in brackets times A is equal to B times A plus B times C. So
absolutely, yes.
Okay.
Sorry, yes, okay. Absolutely. Let me add that here. Thank you.
Okay,
Normally, so everything that we're going to do in this class is going to be commutative rings. Oops.
Okay, so the first one is only required. So if it's commutative.
Yeah.
Okay. My second question was, like, I'm not sure if this is exactly relevant, but like, you know, the equivalence relation, like modulo n, like can it be extended to an n that is not necessarily a natural number? So as to, like, instead of partitioning the integers, you can partition the reals instead, like into like similar equivalence classes. Is that something that's commonly studied?
Yeah, there is. You can definitely do that. So if you take the real line, okay, then if I take 2 points in the real line, I'm going to define an equivalence relation. X is equivalent to y when what? What do you want the equivalent relation to be?
Well, I suppose we could have x minus y is an integer multiple of our n element of reals. So
you want to pick an element in the reals.
Yeah, and then k would.
I don't like to call it n, so I'm going to call it r.
Sure. Okay.
And I'm going to define the equivalence relation twiddle r when x minus y is an integer multiple of r, where k is an integer. Okay, this is a perfectly good equivalence relation.
Okay.
And it means that 0 will be equivalent to r, which will be equivalent to minus r and to 2r and so on.
Okay.
Okay, and what happens here? Well, every number between 0 and r, right, will be equivalent. You know, every single number will be equivalent to a unique number which lies between 0 and r. Right. So, and if you move from 0, start here, and you just walk along, then you're going to find that as soon as you reach r, you're going to be equivalent to 0. So what this really is doing is it's curling it up like this from 0, 1, 2, all the way to r. So it's making a circle.
All right, and I assume that. Oh, sorry.
Let me just. So this is called r mod rz.
Okay, I see.
And this is another way of writing the circle.
Oh, okay, I see. Okay, so I suppose that this would have like use in like
It's okay. Can you just think about it, and let's move on to another question?
Sure. Yeah. Okay, thank you.
You're welcome.
Okay, so Shuo has a question.
Yeah, I have a question about why the field should accept 0 for the multiplicative inverse.
Right. Yeah, that's a good question. So there is a. So this is it's a major issue. So so whenever you start with a set, and you start to equip the set with various operations. Okay, so you're going to say, okay, I have a set of numbers. I want it to have a commutative addition law. I mean, I want it to be an abelian group. So that's putting some kind of structure on the set, and it's giving it some abilities to do stuff. And then you impose another structure. So then you say, I also want it to be multiplicative. I want there to be a multiplication, and I want the multiplication to be compatible with the addition, right? So you're starting to get very crowded. You're starting to have a lot of structure. And the point is that if you put too much structure, so if you say, I want this set to have a binary operation, and then I want it to have another binary operation, and then a third one, and then I want all three binary operations to be compatible. I mean, you could imagine something very complicated, right? With many structures, and they're all compatible with each other. So the problem with doing that is that the more you require, it's like ordering at a restaurant, right? I want this, I want this, I want this. At some point, there's going to be so many requirements that it will be impossible to satisfy all of them, that there will be no sets that even have that operations, right? So this is what happens. So if you require that every element has a multiplicative inverse, then what happens is that it's too much to ask, and you get collapse. Everything starts to collapse, and you get no examples. So let me give an example of this. So in a ring, too much structure can result in no or very few examples. Okay, so just to give you an example of this. Okay, so in a ring, we have an additive identity element, but we also have a different element, a separate element, which is the multiplicative identity element. So we have two distinct identity elements. Okay, and so you could say, well, is it possible that they are the same? So is it possible they coincide? Right? Why do we need to take an additive identity and a multiplicative identity? What if we had both being the same element? Right? So this leads to the following problem. So if it were the case that 1 is equal to 0, meaning that the identity element for multiplication is equal to the identity element for plus, then we want to, what I'm claiming is that we're going to get something funny happen because of this assumption. So if I want to see what the consequences of this are, right, notice that I'm talking about two operations, plus and times. So in this statement, we have, we're basically using both of the binary operations. So there's another law that both of the binary operations must satisfy, and that's the distributive law. The distributive law is another law that would have to relate times and plus. So now let's combine this assumption with the distributive law. Then you see from the distributive law, this says that if I take 0 and I add 0, right? 0 is the additive identity. So when I add 0 to something, it doesn't change it. So this must be 0. So I'm using here the fact that 0 is an additive identity. Okay, but this would mean, so if star were true, star would imply that 1 plus 1 is equal to 0. Because if 1 is equal to 0 and 0 plus 0 is 0, then it must be that 1 plus 1 is 0. I'm sorry, that's also true, but I wanted this one. 1 plus 1 is equal to 0, but 0 is equal to 1. So I get 1 plus 1 is equal to 1. Okay. But then we have the existence of additive inverses. All right. So there is an inverse, minus 1 plus 1 is equal to 0. gives us, so I can add -1 plus 1 plus 1 is equal to -1 plus 1. So now I'm just adding -1 to both of the elements in the equality. I'm adding -1 to the left side and I'm adding -1 to the right side, right? And this gives us 0 and this gives us 0. And so this implies that, sorry, what am I getting at? Oh yeah, sorry. I did nothing. So I just get 1 equals 0 back. Sorry. That's not what I want to do. Sorry. Let's see what happens. So let's try to get something else. So let's consider an arbitrary element A. So A is any element, right? Right. And then I get that I just get that A multiplying 1 plus 1 is equal to A multiplying by 1. So I'm multiplying this equation by any element A. Okay. Now, 1 is the multiplicative identity. So this is equal to A. Oh, I'm sorry. I'm making it too complicated. Sorry. Let's just start again. If 1 is equal to 0, then you get the following stupid fact. So any element A is equal to A times 1 because of the fact that 1 is a multiplicative identity. This is a multiplicative identity. Okay, but this, because 1 is equal to 0, this is equal to A times 0. And this is equal to A times 0 plus 0, which is equal to A times 1 plus 1. And this is equal to A plus A. So this implies that A is equal to A plus A. But because of the existence of additive inverses, so if we add minus A to this, we get 0 is equal to A. So this is telling us that if we assume that 1 is equal to 0, then it automatically will hold that every element of your set is equal to 0. And what that means is that the set, there's only one possible example, which is the set containing a single element. So this would tell us that the set R is just the set containing a single element. Okay, and so this would mean that you would have a beautiful set of axioms. You'd have all this structure, you would have all these operations, but the only example would be the set with one element. So this is the reason why we don't want to allow 1 to be equal to 0. We want these to be different elements inside the ring. A similar thing will happen in the case of fields, okay, that we don't want to assume, so in a field, another example of this, in a field, we want existence of multiplicative inverses for all elements except the additive identity, 0. Okay, because if we did have so if we did have an element R such that R times, we're in a field. So in a field F, let's call the field F. So let's say we had an element in the field such that X multiplied 0 to give 1. So this would be a multiplicative inverse for 0. So if this was possible, if you did have an element where this was true, then well, then we could get the following bizarre facts. So we could say that yeah, so we could say the following. So we could say that 0, I mean, the problem is that 0 multiplied by any element, so for any element inside F, when I multiply 0 against Y, this is the same thing as multiplying 0 plus 0 against Y. And then by using the distributive law, I'm going to get 0 times Y plus 0 times Y. So I get this equality that whatever this is, 0 times Y, it must be equal to itself plus itself. But we have every element is supposed to have an additive inverse. So that additive inverse can be used to cancel one of these out. So existence of additive inverse of 0 times Y implies that 0 is equal to 0 times Y. So in a field, it's always true that if you multiply 0 times any element, we'll get 0. Okay, so this is a general fact in any ring, that multiplication by 0 gives 0. Okay, which is something you're familiar with, but anyway, you just need to be sure that you can prove it using the ring axioms, like I just did. But then you see the problem that if x times 0 is equal to 1, we also know that x times 0 must be equal to 0. And so 1 would have to be equal to 0, and then we're back to this example. So x times 0 is equal to 1 implies that 1 is equal to 0, and we're back to the fact that this field must be just a single point, a single element. And so this is not permitted. This is the reason. It's for this reason. To avoid this, we do not assume existence of multiplicative inverse of 0. Okay. So this is the point, is that if you were a computer, right, and if you were searching for mathematical structures, what you would do is you would say, okay, let's assume that I have one set and let's put some operations on it, right? And so you'll start maybe with, you might start with unary operations or something, but at some point you'll get to a set with a binary operation. And then you'll try to see, if I assume certain axioms and certain laws, right? You could just try to write down all possible laws, and then once you have a selection of laws, then you could look for examples. How many examples can I find? And typically what happens when you play this game is that if you don't have enough structure, then you have tons and tons of examples, and they're not really that interesting, perhaps. Okay, and then if you have too much structure, then you have no examples. So you need to find something in between, which has just enough structure that it will be useful and interesting, but not so much structure that it constrains it to be trivial. And that's what people have found over a couple of 100 years, is that you have things like groups. That's a really big one. that is really interesting and that people were able to classify all finite groups. There's a complete classification of those in the mathematical literature. And then you have rings, which are studied. That's the subject of most of algebra and algebraic geometry. And then you have fields. And what you see when you go from groups to rings to fields is that because there's more and more structure, they become highly constrained. So for example, fields are extremely constrained. Even though they are more complicated, they have more structure, but there's not as many examples of them. I mean, there's still infinitely many examples, but I just mean for finite fields, they're quite constrained.
Okay. So if there is a real number and plus infinity, and if we define that 0 multiplied infinity can be any numbers, could it be right?
Let me see how to answer your question. So you see, look at the argument that I gave. You have to think about the argument that I gave, right? So I'm saying that if you have a field, and if that field, what was the argument that I gave? What I explained is that if you have an abelian group which has a binary operation on top of the additive one. So if you have an abelian group with a multiplication operation, which is associative, okay, and distributes over the addition, and if you have an element which is the additive inverse for 0, then it forces 1 to be equal to 0. I did not assume that we were in the real numbers or that we were in the real numbers adjoint, with the real numbers union infinity where you add an extra point. Okay. I didn't make any assumption about what particular case you're in. If you have an abelian group, right? And then if you insist that all elements will have multiplicative inverses, you're going to run into this problem, and the argument holds.
Right.
So you see, like, I gave you the proof in general, but then you tried to get around that. You tried to say, oh, but what if I introduce a new number which is called infinity, and if I try to define the operations to include infinity and so on, then isn't that going to work? Then 0 times infinity will be equal to 1 or something. But it's not the case, because I gave a general argument why the thing will fail.
Right. Thank you.
You're welcome.
All right, so there was a question by someone, but they had to leave, so they wanted me to ask on their behalf. So they were wondering if tutorials could be recorded and posted on Quercus.
Okay, so the reason that we're doing the tutorials without recording is because we want people to be completely free to ask whatever they want without having to be recorded. So that's the reason that we're not recording tutorials.
Okay. All right, so Michael has a question.
Hi, so it's about fields. I know you said, well, I know you're going very quickly, so I just want to clarify. You said that fields are basically rings in which any element has a multiplicative inverse, except 0.
Correct.
So I read also online, though, that it seems fields require that the multiplication, quote unquote, is commutative.
Yes, that's right. Yes, that's
Okay.
right. Yeah, originally when I was preparing this lecture, I was going to do commutative rings, but I kind of skipped that. So
Okay.
absolutely right. Yes.
And then I have another very quick
number
question.
1,
Yep.
the multiplication is commutative. But I'm going to do this. I'm going to go over fields in detail on Tuesday.
Okay. And then,
Yeah.
so I just have another very quick question. So what you were doing after defining the addition mod 10 or well mod n operation, so is that basically the same as conceiving the binary operation as a function, because it is a function, and then showing that function is well defined? Is that basically all the work that you were doing in green after this stuff right here, the 1 and 2?
Yeah. So it's I agree with you. Yes, that's correct. But I wanted to avoid phrasing it in the incorrect way in which you phrased it. Okay, why do I say that? So you cannot have a non-well-defined function. That doesn't make any sense.
Right.
Okay, so it's not like there is a function and then I need to check that it is well-defined. No, the problem is to define the function in the first place. I'm not checking. You see what I'm saying?
Mm-hmm. But so the reason though that I say that is because I've seen like in other classes, like if I just introduce some random thing and I try to claim that this is a function, I have to show that it's well defined. And I thought this is kind of like
that's correct. That's correct. But that random thing which you introduced should not be called a function or a map.
I should rather call it maybe a relation, right? Before it. Would that change anything?
No, I mean, an equivalence relation has a bunch of axioms too. So the it's
not an equivalence relation, but like
the point is just that you have a procedure, right? You define a procedure, and then you're trying to show that that procedure is actually a map.
Okay.
It's not quite a relation, but I mean, I don't want to formalize it. It's just like an algorithm or something. Like you say that, given, like, for example, in this case, you say, what is this, right? So of course this, what this says is that if you want to define the addition of these two classes, then you should choose a representative of the class, choose another representative of the class, and then add them together and take the class of that.
Right.
So, so you could say that it is a, you could say that it is a relation, but not an equivalence, an equivalence relation, just a general relation. You could just say that as long as you have an integer and another integer and a third integer, I mean, the point is that you're checking that you do have a map, right? You're checking that a certain procedure, which involves choices, actually defines a map.
Okay, I see.
I don't really want to formalize it too much, but I just don't like the terminology where people say, I need to check that my map is well defined. I mean, that doesn't make any sense.
Right, I see. All right, thank you.
Okay, so Jay has a question.
Hi. So when we tend to think about groups, or at least I guess what the definition, so groups tend to encode some form of symmetry, right? Like you can have a set that is some kind of rotations of a geometric object that's symmetrical about some axis, right? So when we consider the abelian group, where is the quote unquote symmetry encoded in that? Some other group.
Good question. So I mean, the motivation for the introduction of groups way back when was indeed that, if you have a mathematical structure, then you can look at maps, bijections from this object to itself. And like we explained before, the bijections from a set to itself forms a group. And so that is a general idea that if you have some object, then the symmetries of the object or the bijections from the object to itself, those form a group. So it's a source of many groups. But the notion of a group is an abstraction of that, and these groups don't necessarily have to be realized as bijections of some other thing. You should think that the idea of a group is just the abstraction of the idea of a symmetry. Okay, now on the other hand, you can always let a group, you can always think of a group as the symmetries, certain types of symmetries of itself, because any element of a group, you can use that element to multiply all the elements in the group by that guy. Right, so if you fix an element in the group and you use that element to multiply everything else by that, right? So let me just explain what I mean. So suppose that you have a group G. So if G is a group and little g is an element of the group. Okay, so if we fix G, fix an element in G, then we can use this to define a map. Let me call it LG. Okay, and this is a map from G to G. What does it do? Well, it takes a random point, any point in G, and it will send it to G multiplied by X on the left. So this is called left multiplication by the element G. Okay, that's the map. So every element can be used to manufacture a map from G to G. Does that make sense first?
Yes, I think so. Yeah, so you can make like a certain number of these maps, or you take every element, fix it, and then multiply it by each other element. Sure. Like
yeah, for every element, we have a map. Okay, and the interesting thing is that this map is a bijection, or is invertible. So what is the inverse of this map? Okay, so if I have a map that takes an element to G times the element, what would be the inverse map? Let's say taking Y.
So you'd have to divide by G, or 1 over G times 1 over G, right?
Yes. So what is that? What does 1 over G mean? It means the multiplicative inverse
of G,
right? G, which exists because we're in a group.
Okay.
Right? So G has an inverse. So what would I need to do with that inverse? So if I'm starting with Y, what do I need to do? Let's say, so G has an inverse, G inverse, I'll call it. And so what should I do with this G inverse? I should take Y to what?
You're taking Y back to X.
Well, I want to know what my map does to a general element. So what should I do to Y?
Oh, multiply it by 1 over G? Or, oh wait, you said left.
So I'm not using the term, I'm not using the old-fashioned language 1 over G. I'm using G inverse.
G inverse, okay. So left multiply by G inverse?
Thank you.
Okay.
Yeah. So we left multiply by G inverse, and we get G inverse times Y. Right? And if you check, apply the first map, it'll take X to G, X, and then if we then apply this map, it'll be sending it to, if I take LG applied to X, and if I take LG inverse applied to that, this will be LG inverse applied to GX, and this will be G inverse applied to GX multiplied here. And then I can use the associative law to write it as G inverse GX. And then I can use the definition of the inverse to say that this is equal to the identity element times X. And then the fact that E is the identity means this is equal to X. So we get that these two are, they're opposite, they're inverse to each other. The composition takes X to X. And then I could do it in the opposite order, and you could see that it's also true in the opposite order. To check that it's an inverse, I need to do both. So this means that this shows that this one here shows that LG composed LG is equal to the identity. And this one shows that LG composed with LG inverse is equal to the identity on G. So these two facts tells me that the answer is LG inverse. Note that there's another thing you can do. You can also right multiply by G. There's also the right multiplication by G, which takes a general element and sends it to XG, where you multiply on the right. Okay, so if we take, let's say we take as an example Z mod 3Z, or Z3, like I said. So Z3 has three elements, 0, 1, and 2. Okay. And if I act by the group multiplication, the group law, let's say if I do L 0, where will 0 be sent? If I do left multiplication by 0.
Left multiplication by 0, I guess it would be 0.
Yeah, but keep in mind that I'm not really multiplying in the usual sense. The group law is addition here. Oh, addition modulo 3. So 0 plus 0 is going to be 0. What about 1? Where is 1 sent?
So I guess 1 is sent to, is it not just sent to 1 in this case?
Don't ask a question as an answer. Just answer.
Okay, 1 is sent to 1.
Yeah. What's the worst that could happen? You could be wrong. What's going to happen if you're wrong? 2 is sent to 2. So this left multiplication by 0 is the identity element, is the identity bijection, right? What if I do, if I act by the element 1, if I multiply on the left by 1, multiply really means add, because that's what the group law is here. Okay, what will this do? I just add 1 to everything. That's the map. So what's 0 plus 1?
You'd have 1.
And 1 plus 1?
Have 2.
And 2 plus 1?
Then you have 3.
3, but 3 is equivalent to 0.
Right, because it's mod 3. Oh, okay, so it goes to 1 or 0.
So this is the bijection that we get for the action of 1. So the element 1 has been promoted to a bijection from Z3 to itself. And what is it doing? It's just rotating the 3 points, right? If I write 0, 1, and 2, okay, L1 is just doing this. So you could think that the group, the elements of the group, are actually symmetries of the group itself. Okay, that's that's a little bit tricky to make perfect sense of, but I just wanted to show you this as a kind of partial answer, that groups, when someone gives you a group, it doesn't make sense to ask what is that group the symmetry group of, because the group is an abstraction. It may be the symmetry group of many things, or it might be the symmetry group of nothing.
I see. I kind of see. I guess my impression was, I guess I thought that was like the reason we had it, but so it doesn't. I mean, I'm sorry. The reason we had a group was to express some kind of symmetry, but it's not necessarily.
It's not necessary. Yeah, the idea of a group is a more fundamental concept, and symmetries they're really about two things. In order to have symmetries, you need the group, and you need the thing that the group is a symmetry of. So you would really need two sets. You would need the set that is the group of symmetries, and you'd need the set that the symmetries are acting on. And so it's a more complicated idea than just group. Group has only one set, which is the group itself. So you could say it like that a group is a fundamental ingredient in the idea of symmetries, but it is not necessarily symmetries of something.
I see.
But on the other hand, what I said is also true, that you can actually, if you wanted to really be pedantic, you could say that the group is a symmetry. The elements of the group are symmetries of the group itself, just like the way that I just said. But that's kind of like, yeah, I mean, that's a clever thing, but it's not, I mean, it sounds like exactly what you were thinking of.
Sounds like you can say that for any budget, like any set, I guess. If you consider this a symmetry, it almost seems like you can say that for any set.
No, you know, in order for this LG to be defined, you really need the group laws. So it's special.
Oh, right, because you need it to be. Right.
It is special to groups. Yeah. Okay. Anyone else?
Bo Tao has a question.
Oh, we have Professor.
Hi.
My question is that what's the formal definition of the classification? Why don't we just use the word subset?
Sorry, I never gave a formal definition of classification or anything like that. What are you asking about?
Let me introduce the equivalence relation between the integer modulus.
So you're talking about when I was talking about equivalence relations?
Yes.
So whenever you have a set, you can define an equivalence relation on it, and that will break up the set into a partition, and all the elements of the different sets in the partition, those are the different classes, the equivalence classes, and that's what a classification is. A classification is a partition of a given set. So I talked about partitions, and I talked about equivalence relations, and those are essentially the same, right? Because an equivalence relation it divides whatever set you're considering into different equivalence classes, and those classes are giving a partition. So it's like dividing all the animals into different species. That's a partition of the set of animals, and it's a classification, therefore, of the set of animals.
Okay, got it. Thanks.
Okay.
Okay, so Dihan has a question.
Hi, Professor. I just wanted to clarify a couple of things about cycles from the last lecture.
Yeah.
Go ahead. Could you go to that page, actually?
Just what's your question?
So it was about the labeling of the cycle.
Yeah.
Where we labeled x to 1, fx to 2. So I just want to clarify, is this a labeling from BK to BK? since F was defined as BK to BK.
So are you asking about the cycle notation, or what exactly are you asking about?
Like the labeling, where
the labeling of what?
Is that cycle of the cycle? Is that cycle notation where X is labeled as 1, Fx is labeled as 2, and f of X is labeled
Okay,
as 3?
I'm not really sure what you're asking, but let me just give you the basics, and then you can ask based on what I'm about to say. So you agree that this set is B5.
Yes.
And here we have the same set, B5. Okay?
Yes.
So I'm going to consider maps from B5 to B5. Okay?
Yeah.
And the map that I'm going to define, I want it to be a bijection.
All right.
So there's many possible bijections from B5 to B5, but one of them might be like this. Do you agree that this is a bijection?
Yes.
Okay, so f of 2 is equal to 4. F of 3 is equal to 2. F of 4 is equal to 5, right? I'm telling you what the values of all the... Okay, so suppose that I wanted to write this bijection. So any such bijection from Bn to itself can be written. Okay, I wrote it already in one way, but you can write it in a different way in cycle notation. How does it work? Well, you have to start somewhere. So you start with 1. And where does 1 get sent? You tell me.
2, 3.
Okay. And then where is 3 sent?
2.
And where is 2 sent?
4.
And where is 4 sent?
5.
And where is 5 sent?
Back to 1.
Therefore, I put the parentheses. That's the cycle notation.
But
just one second.
My question is...
Just 1 second. It's not just for you, it's for everyone. Let's say I do this. One is sent to 3. 3 is sent to 4. 4 is sent to 1. So I have a cycle, I close it. Then I need to open a new cycle. So you can start anywhere you want, it doesn't matter. Let me just choose a starting point which hasn't been covered already, like 2. So 2 is sent to 5. 5 is sent to 2. So I've completed the second cycle. So this bijection, G, has 2 cycles in it. So it's a different type than F. In the classification of bijections, it would be in a different class because the shape of the cycles are different. Okay, and it doesn't really matter. It doesn't matter. I could write it alternatively like this. I could write 3, 4, 1, 5, 2. This would be exactly the same because the whole point of the cycle notation is that it tells you 3 is sent to 4, is sent to 1, is sent to 3, and so on. So it's giving you the cyclic behavior of the map. And it also doesn't matter which one I put first, right? I could put 5, 2 here and 3 and 4, 1, 3 here. These are all the same element of the set of bijections. It's just a shorthand notation for the maps from a set to itself. Yeah, okay, now ask your more special question.
No, there was just something in your notes that confused me that day.
Okay.
If you could scroll up to them. So yeah, here. So in the last part, in a cycle, we can label x to 1, fx to 2, and so on. So my question is, can we call this a labeling from bk to bk?
Where is it? Labeling is just a map from a set to B of the same cardinality of that set. Right? So it's a bijection from a given set to B3, which assigns a label, a numerical label, to every element of the set.
Right.
So if X was like, if I had a set consisting of animals or whatever, and we had a bijection of the animals, so we were moving them around, right? Then you could just label the first, label whatever animal you're interested in as 1, and then wherever that one is sent, you label that 2, and so on. So I'm just saying that whatever the cycle is for whatever set it is, right? A cycle means that you can find an element. You start with an element. It could be up to you. You could take any element you wish, and then you keep applying the map. And all of the things that you obtain, you put them all together in one set. That's a cycle. Okay, and if you wanted to write this cycle in cycle notation, you would have to label these elements, whatever they are. X would be labeled by 1, f of x, you could label it by 2. If you chose that labeling, if you labeled this as 1 and this as 2 and this as 3, then the cycle notation would just be like this.
Okay.
I mean, it's not, the important thing is what I explained here, right? That the purpose of cycle notation is to write down this type of diagram, which tells you where 1 is sent, where 2 is sent, where 3 is sent. Instead of listing, another way of writing it could be like this, that instead you might, an alternative notation for the map F would be like this. You just label all, you just list, or you actually, you list all of the ordered pairs. So you list 1 and where 1 is sent, which is 3. You list 2 and where 2 is sent, which is 4, right? And then you keep going, 3, 2, 4, 5, and 5, 1, right? This would be the kind of brainless way of labeling, of writing down this map. You just write down every point in the graph of the map. This would be recognizable by a computer, that's fine. But a more efficient way would be to just write down the cycle notation. Because then 1 is sent to 3, 3 is sent to 2. If anyone asks, where is 4 sent to? You just look for number 4, 4 is sent to 5. Rather than to search here, and then you find 4 and sent to 5. So the concept here is bijections from Bn to itself. And then there's just language, which is the notation of how it's represented.
Okay, yeah, I got it.
Okay, we gotta stop. So so everyone should just realize, I hope everyone understands that Piazza is really being used. So you should really go on Piazza, but I guess the people who are here right now probably do use it. Okay, have a good weekend. See you on Tuesday, and enjoy assignment number 2. Thanks a lot, Syed.
Yeah, no problem.